we're going to have 6 modules for this, and each of these modules is going to introduce you to a class of design patterns. And then within that class, we'll discuss a variety of design patterns which fall into that class. So for example, in today, we are going to spend some time in doing some introductions, and introduction is going to be about why we require the MapReduce. And then we come to the first design patterns type, and that's the summarization patterns, which we'll talk about today. Module 2 is going to be about the filtering patterns, and then so on and so forth, as you see things listed down here. Okay, so the objective of the module today is to look at the why and the what of design patterns, MapReduce design patterns. So as far as why is concerned, we should understand initially as to why we actually require these design patterns in MapReduce. And that's where some of the constraints and some of the facilities which the MapReduce design patterns provide us to be able to design in ways from which these patterns actually emerge. And then, of course, as I said, this class is actually about the first set of design patterns, which is the summarization patterns. We'll talk about that. And then in the end, we'll look at the project details, because as I said, the project is going to be a significant part of this course. So it's important for you to pay attention and do these projects well to gain full benefits out of this course. Okay. So before I get started with the design patterns itself, let's do a quick review because in the introductions I found that there probably is the class is on a continuum. People have just started on the side of MapReduce, and there's others who have quite some experience in this field. So I'll just revise quickly without putting too much time on this. So broadly, if you look at the MapReduce framework, the task can be divided into 2 different categories. So we have the map side tasks and the reduce side tasks. What is included in the map side tasks is the record readers along with the input split and those things. Then you have the mapper, the combiner, the partitioner, and broadly classifying on the reduce side, you will see the shuffle, sort, reducer, and the output format. Okay, now let's understand these things a little bit in detail. I'm sure it's for some of you it's just a repetition of your past stuff, but just to put the context here, I'm going to explain a little bit about these. So record reader, so this is stuff which is responsible for reading from the input split, and what actually the record reader reads is the bytes, and is responsible for dividing those bytes along records, and that's the input which the mapper gets. Now the mapper is the job which is responsible for performing. What you do in the mapper is you pass the data, you filter the data, and an output from the map is key and the value pairs. Okay, now these key and the value pairs are not very arbitrary. Okay, they're very much dependent on the kind of problem you're trying to solve. Okay, and as you will see in the design patterns that I discuss over the next couple of weeks or 3 weeks, you will see that manipulating these key values, by manipulating these different patterns emerge. And it's important to understand these things in slightly deeper ways. Then we have the combiner, and combiner. So this is something which is important aspect of a lot of design patterns. So in some cases, the combiner might not be very useful, but there are other cases where this can be very useful. So patterns or problems where you have a lot of data being transferred across the network from the mapper side to the reducer side. You should definitely have a look at using the combiner if the problem is such that you can use it over there. you can get benefits out of some combiners, but there will be cases where combiner might not be useful, and we'll see in which cases it's useful and in other cases where it's not useful. Then the partitioner, this is one of the controls which this framework provides you, and the default partitioner is the hash partitioner, which just hashes your keys and does a modulo on the number of reducers, and your key values get transferred to the reducer side. But there is a way for you to write your own custom partitioners, and we'll see in some of the design patterns where writing such things is going to be useful for you. Look at the shuffle side here. Okay, so once a partitioner has done the partitioner on the data collection which is coming out of the mapper, it puts that stuff onto the local disk on the mapper side, and then the reducer for which the data is meant actually pulls that on its own side onto its own machine. That's the shuffle. Then you have the sort phase. So after the shuffle, the sort happens, and in sorting, again on the reducer side, based on the keys, the data is sorted whenever it's going to be input to a reducer. There are certain important things to consider here, which we generally tend to miss. So when you talk about partitioner, when partitioner is doing the partition at that time, it actually also runs a sorting algorithm, which is which actually takes a raw comparator. Okay, and in some of your patterns, you will see that by using and implementing your own raw comparators, you can influence the behavior of the way the things are sorted. Similar thing actually also happens on the reduce side. Okay, so there is a raw comparator which you can implement on the reduce side as well, and that helps in some of the sorting patterns that we'll see. Then the reducer, and this is where most of your analytics and the actual crux of the work happen. And ultimately, the output from the reducer is put to the HDFS by this output format. So that's a very quick summary of what the MapReduce design pattern components are all about. And I just wanted to emphasize a little bit because these are the tools in your hands. When you're writing MapReduce programs, when you're writing, we're trying to learn about design patterns, these are the tools that you'll have, and you will have to manipulate these in some ways to be able to achieve your objectives, and that's what those design patterns actually do. Okay. So the question is, why do we require MapReduce design patterns? Okay. Let's attack this problem with a simple question. Okay, now generally when you have to do a sorting, and when the sorting is not on a big data, what you do is you go ahead and use quick sort, much sort, one of these standard algorithms, and they do a perfect job for you. Now when the size of your data really increases to the proportions of big data, then you have problems using those sort algorithms. Just think, can you use quick sort or a merge sort to do sorting on MapReduce? It's maybe we can try to do some things on this, but you will immediately start hitting some roadblocks, and the first one you will find that MapReduce is not an iterative framework. Okay, but the thing is we can still implement iterative algorithms on this framework, but by default it's not an iterative framework. There is a mapper on one side, you have the reducer on the other side, and that's it. I mean, the inputs come into the mapper, reducer writes to the output, and your job is complete. So you don't really have an iterative framework here, and all those algorithms we were talking about, quick sort, merge sort, they require some iterative framework. Okay, so the framework, as you see, is putting restrictions. So there are constraints as far as the framework is concerned. You cannot go beyond what is provided by those frameworks. You have to work within the limitations of that. Okay, let's see what these constraints are. So there are rigidly defined stages that must work together in specific ways. So when we saw all those tasks which happen in the map stages and the reduce stages, you could understand that there's a rigid way of operation of this framework. But still, as I said, many algorithms can be recast to this framework, and then you can solve your problems at scale. Okay, and that's one of the places where MapReduce patterns will come in. Other constraint is the synchronization which happens only at a single opportunity here, right? If you look at this whole job, the opportunity for doing a cluster-wise synchronization is happening only at one stage, and that is during the shuffle and sort stage. Otherwise, your mappers, reducers, any of the other processes that you have inside there, they actually work independent of each other. If you think deeply, then these are constraints. These are constraints, and that actually ends up being that ends up telling you that the programmer has very little control over many aspects of the execution. You don't have much of a control as to where a mapper or a reducer runs, when a mapper or a reducer begins or finishes, which input key value pairs are processed by a specific mapper, which intermediate key value pairs are processed by a specific reducer. Constraints are making sure that the programmer, as I said, right, doesn't have much of a control in terms of the execution. So they have to work within those constraints. But it does provide you a lot of techniques, a lot of ways of getting around these and solving really complex problems using whatever it provides. So let's see what it provides. So the ability to complex data structures as key and value. Okay, and we'll see in some of the examples of the design patterns how just by way of creating complex data structures, you can solve problems which would have looked like unsolvable without having those complex data structures. Other things which it provides is user-specified initialization and termination code at the start and the end of MapReduce jobs. Ability to preserve a state in mappers and reducers across multiple input or intermediate keys. These two are important things. There are times, and we'll see one of the examples in this lecture itself, where you want to have some data structures which needs to be preserved across calls to mappers and reducers on different inputs. So this facility helps in some of the design patterns that you'll see. Ability to control sort order of intermediate keys. Now this is something which you get by the raw comparator talking about earlier, and this is very important in cases where you want to do secondary sorts or you want to do a join on the reduce side. This facility comes into picture at that point. Ability to control the partitioning of the key space, and this is also pretty important. By writing your own partitioners, you control the working of a few of these patterns. Okay, so what is the answer that we got on why do we need MapReduce design patterns? Because of the constraints that we saw in the earlier slides. And the patterns help you solve problems, and there are people who have already learned to solve those specific problems in certain ways. So it's good to use those patterns in those ways. And then there are cases where there are scalability and efficiency concerns. So it happen that you go ahead and write a completely fine working program, but then in the end you will find that the program has scalability issues. So some of the patterns actually address that. So learning that is going to be useful for you. So here are the different design patterns on this slide. And I'll give you a brief overview of these. These will be covered as part of the module in the subsequent classes. So today we'll discuss the summarization patterns. These are the patterns which use when you want to have a high-level view of the data. So in a lot of analytics tasks that you do, the first thing that you do is trying to understand the data from a very high level. And that's where summarization patterns come into the picture. We'll see examples of this in this class. Now you have the filtering patterns. So summarization pattern, when they are giving you a high-level view of the data, they're actually calculating some kind of a statistic on top of that. Okay, what you ultimately get out of it is slightly different data than you had originally. Then you have filtering patterns. By the name, it does say something. So in filtering patterns, the idea is to filter a subset of the bigger data set and something which is more interesting. You filter those things out and perform further analytics on those things. Filtering patterns, which we'll talk about tomorrow, is going to be about that. Data organization patterns. In these patterns, let me give you an example. So these patterns don't exist in isolation. They are part of a bigger system. So it could be that you have a system which deals with more unstructured data. So a data which is more in hierarchical form. So for example, if you take Twitter data and then you try to combine this with some data which is coming from a structured source, in such cases we'll go ahead and use a data organization pattern. What happens in those patterns is you might have a set of sources of the data which is very structured, and then systems that you have down the pipeline, they need more hierarchical data to be able to do efficient computation on them. So that's where you will go ahead and use patterns regarding data organization. We'll discuss the join patterns. So in joining, you get more value of the data when you combine the data which come out of two different sources. So that's what join patterns will be about. We'll discuss different cases in that. Meta patterns, they are not really patterns in the true sense of the word that we have seen so far. Meta patterns are actually more about job chaining. Okay, so providing more job control to you by doing the job chaining. That's what meta patterns are about. And they're going to be useful in trying to implement, if you're trying to implement a graph algorithm using MapReduce, then these patterns will also come into picture. Then you have the input and the output patterns. They are customizing some of the way you read your inputs into your programs and customize outputs that you write to the output. Graph patterns, these are very interesting patterns, and you will also be doing a project on this. So the different, so for example, the page rank algorithm, and that's one of the modules in your project work. That graph pattern, the page rank algorithm will implement here. And then we have others here, for example, pairs and stripes. So pairs and stripes is useful in cases of text analytics. For example, we calculate a lot of bigrams and trigrams when we are doing analytics on text. So pairs and stripes are useful in such cases because they output pairs of words which are adjacent to each other. Okay, so after those introductions, we finally come to the first design pattern, the class of design patterns rather, as a summarization pattern. Okay. So as I said, these patterns provide a very high-level aggregate view of the data set when visual inspection of the whole data set is not feasible. Okay. Now the people who are new to big data, or for example, for yours, statisticians and analysts, have been doing this kind of aggregate view of the data, and that's probably the first thing they do when they have a look at a data set. Try to understand a few things about the data before they go ahead and do further things in this data, more interesting things. Okay, so summarization patterns comes into picture over there. Okay, now why do we require a pattern for that? The reason is, although this stuff might look very simple, and some of the examples I give you will be very simple, the thing is trying to understand how such things can be implemented on this framework is going to be useful, and we'll see in the examples here. Okay, so they are responsible for doing, they group on keys, and then on those groups they calculate some statistic. Okay, this could either be calculating a statistic or indexing that data, or it could be counting. But there is a connotation of summarizing in some ways on a group of data. Okay, so some of the examples, quick examples, would be number of hits per hour per location on a website in a weblog. Okay, so you want to understand per location how many hits are there on your website. So and then based on that you want to do further analytics. You want to do some kind of campaign on from where more users are coming. So on those locations you will take further action. So the starting point for that would be a summarization pattern. And there are a few more things that you can do with this. Average length of comments per user in blog comments. Now this will help you probably understand which users are contributing more to the comments, which are more active in terms of following your blogs. So we'll talk about three different summarization patterns. One is the numerical summarization. The other is going to be counting with counters and inverted index. When you will see this, you will realize that most of the stuff which is talked in this, some of these problems, so for example, look at inverted index. It's a complex problem, isn't it? So for example, Google maintains an inverted index for doing retrieval of your queries. Now, you will see in some of the slides when we come to inverted index, you will see that doing this on MapReduce is very simple. It's very simple. And the reason for that is the whole framework itself provides you that facility. The facility of grouping by key is a very core functionality which a lot of these design patterns will use, and that tends to result in very complex algorithms being implemented pretty easily. Okay, so you will see that inverted index is one of those. We'll see numerical summarization and counting with counters when we come to that. But the important thing to keep in mind is these are a straightforward application of grouping by key functionality which the MapReduce paradigm provides you. Okay, so in numerical summarizations, you do some of these tasks. You find a data set, you minimum, max, you find sum of that, average, median, standard deviation. Again, the initial tasks that an analyst probably will perform on a data. One important thing to keep in mind when you work with numerical summarization patterns is to use the combiner properly for efficient implementation. See, when I was explaining to you some of the stages in MapReduce execution framework, we said we if you use combiner properly, some combiners can be used in some cases in some design patterns for effectiveness. Now this is one of the design patterns where you can use it very effectively, because if you use a combiner and because you're calculating a statistic which is an aggregate data, you tend to transfer much lesser data over the network from the mapper side to the reducer side. If you don't use a combiner, all the data which is being output by the mapper ends up being on the reducer side. But by using a combiner here, you will find aggregates which you can transfer to the other side, which is much lesser transfer of the data. Okay, some of this applicability which I talk about in patterns might not seem too interesting. For example, applicability here says that you are dealing with numerical data or counting. But these things need to in mind. For example, numerical summarization, you cannot just go and perform on a text. If you're doing counting, some kind of accounting probably you'll do. But if you have text data, probably this pattern would not apply. So it's good to keep these things in mind, although they would seem trivial. The data can be grouped by fields, for example, right? So this again, in terms of the statement itself, it looks trivial. But keep in mind when you're talking of big data, unstructured data, the data can be of different types. So it's important to keep these. Here is a structure for numerical summarization. It's a very simple structure, in commensurate with the fact that this also is a very simple design pattern. So you have the mappers which give you the summary field for each of these mappers, and it goes to the partitioner, and then you have the reducers which actually are doing this summary operation on those fields. In this diagram, we are not seeing the combiner, but combiner can add a lot of efficiency in this. Okay, now one thing to keep in mind is a lot of times we use the same combiner as the reducer. Okay, we write the reducer code and use that as a combiner. Now, you should realize that you can do such a thing only in cases where the operation which you're on the reducer side is actually an associative and commutative operation. If that's not the case, you cannot use that. And that actually drives from the fact that there is a bit of asymmetry in terms of what a combiner can output. So combiner definitely has to output whatever the reducer requires as the input. Okay, so that has to be kept in mind, and because of that restriction, you have to make sure that there is associativity and commutativity in the operation that you're trying to perform, summarization operation that you're trying to perform on the reducer side. For folks who would like to understand a little bit more about this associative and commutative things, so this is actually a concept from algebra. So if you have 3 different variables A, B, and C, and you're doing A plus B plus C, then if this is an associative operation, you could do an addition of C and then add A to it, or you could do A plus B and then add C to this. Okay, so addition operation is an associative operation. It's also a commutative operation, right? If you flip the sides, A plus B and B plus A are the same. Okay, so as far as such operations are concerned, you can use the same combiner as far as the reducer. But there are operations which are not associative and commutative, and we'll see examples of that as well. Okay, so do you need to use a custom partitioner here? Yes, if you feel that there is skew in the data, and one of the questions you probably might have in the mind is, how do I figure out whether there is a skew in the data or not? Because it's big data, I cannot just go ahead and have a look at the whole data. So when we discuss the filter pattern tomorrow, we'll discuss something called simple random sampling. We're doing a simple random sampling on the big data. You come up with a data set. By doing analysis on that smaller data set, you will figure out in terms of the skewness in the data. If there is skewness, it definitely augurs well that you also implement a custom partitioner. What this will do is it will distribute computation uniformly across the reducers. The performance of numerical summarization. So see, the crux of this pattern is grouping by key. Okay, and that's something which, if you're executing any MapReduce job, anything which will run on Hadoop, even a big job, that has to be at that cost. Okay, so let's talk modulo that, and then let's see what will impact the performance here. Of course, if you can use if you're using the combiner or not, that will definitely affect the performance because, as I said, the network traffic is going to be lesser. For skewness in the data, you should use a custom partitioner for improving the performance. And you should also use appropriate number of reducers based on some of the analysis you would have done using the simple random sampling on the data. Okay, so some of the use cases of numerical summarizations. The min-max count. So we'll see an example of this. It's quite apparent by the name itself, so I need not explain that. Average, median, standard deviation. We'll see an example of the average also. And the reason I'll talk about average as well is because this operation, average, is not an associative operation. So we'll have to use a different kind of a pattern to be able to use the same reducer for the combiner. So, and there is another one which, do these patterns have any visual chart like most J2E patterns have? So the visual chart, the structure that I tried to show you is actually a version of these patterns. Okay, fine, then let's move ahead. Okay, so one of the things, so for this course, we are going to use the Stack Overflow dataset, and this dataset is actually huge. For example, I was trying to download data from 2014 Jan till September, and when I actually unzipped all this stuff on my laptop, it went ahead and was actually consuming about 130 GB of the disk space. So probably in this class and in some of the illustrations that we do, we won't be able to use such huge data. We'll use the same tables, but we'll have a stripped down version of those files. Okay, so for this min-max count example, we'll look at the badges.xml file, and this is a file which is about the badges which is given to the users on Stack Overflow. And the task which it's going to perform is for every badge name group. So there are different varieties of badges. So for each of these name badges, we'll see what is the minimum and the maximum date on which the badge was assigned, and also count the number of badges per badge name group. Okay, so if a badge is probably a 5-star, okay, I'm probably this is not a real badge name category. Whatever I'm saying is, if your badge category is, for example, 5-star, what we're trying to see is when was the last time, when was the first time, and when was the last time such a badge was actually assigned, and how many badges actually exist in that category. So all these operations, so again, let's see, the min, max, and the count, All these are associative and commutative operations. So the reducers that we have is going to be used as the combiner as well. Okay, before I come to the demo slide, let's do a quick, this is a data flow for a very small data. So as you can see, you have these group 1 and group 2 users, and this is the map output which you give to the combiner, and then you can see in the reducer input what has been reduced. So for example, if 1, 2, 3, 4, that's the user ID. So the minimum values has already been calculated by the combiner here. So you have 8, maximum is 21, and count is 3. Similarly for group 2, you have the values listed in the table at the bottom over there on the right hand side. And then the combiner wasn't run on the last 2 records, 9999. So they just got passed along as they were to the reducer, and on the reducer side, the min and the max were figured out. Okay. Before I show you the demo, when I run this program, I will show you the code for this. And one thing to keep in mind is the examples which I give for the design patterns would be simple ones. The idea is for you to have these complex, these patterns form in your mind, and then slowly when you get to the project stage, the code that you will write will start getting complex. Okay, so the idea in the classes is to introduce you to the patterns, and then show you that pattern with simple examples, and then you implement the complex thing as part of the project work. Okay, so for this, I'm just showing you. At the bottom there, you see this min-max count tuple, and there's a class object for keeping all those min-max and the count values, whatever is output as a value. So this is what is going to be output as a value. Okay, if you look at the driver code here, they are doing standard things, and because all of you have some experience on the MapReduce side, so you definitely understand what they're doing. Let's go and have a look at the mapper code now. So this is MRDP utils is the utility class, and it reads a value from the XML file and parses that, and then and actually puts this into a map, and then you get the date and the name from that map. So what each data input, what the mapper is doing is trying to do is it's setting a value data, value date, the minimum date for the value, that's what we wanted, and the maximum date for the value, and for each of these it's setting the count to 1. Okay, and all these things, this whole tuple is going to be output as the value for the badge name. Okay, so the grouping on the reducer side will happen on this badge name with these all these 3 values, min, max, and the count, going to the reducer side. Okay, so on the reducer, for the group key, it finds the minimum using the code over here, and then it finds a maximum using the code over here, and then you have the sum of all those records. Simple. I mean, it's a very simple pattern, but it's able to do your initial summarization on the data which you can have a look at and do further analysis on that. Okay, and the combiner can be used here, as I said, because of associative and commutative operations, and we use the same reducer as a combiner. So here it is. The stuff that you see in the first column, these are the badges which are assigned, and you have the minimum dates, the maximum dates, and the count. Okay, so it gives you a summarized view of the data. Okay, just by looking at this now with this data, I can probably see that, okay, yearling is something which has got a lot of batch counts, that's 97. And then very least one, so you can see that's copy editor. Okay, and then I can decide on doing further analytics on that. So that was the purpose of doing a numerical summarization operation. So what I see is what we are trying to do in this example. So in this example, as you can see in this data template here, you have the user IDs, you have these names. These names are actually the badges which have been assigned to users. Okay, and then you have the dates. Does that answer the question? We have this data set on which we are trying to figure out for each variety of badge tags, badge types, what was the first date on which such a badge was assigned, and what was the date on such a badge when such a badge was assigned. And we also counting the total number of badges of that kind. Okay. Okay. We saw in the last numerical summarization example with min, max, and the count, we could have used the same combiner as the reducer code. But when we come to the average example, here also we are finding a statistic on the data. But in this example, we cannot use the same reducer as a combiner. The problem is the average operation is associative operation. Although it's still a commutative operation, but as far as associativity is concerned, it's not an associative operation. Finding an average of 2 numbers and then an average of 3 numbers, and then combining these 2 averages will not get you the average of those 5 numbers combined together. So that makes this an non-associative operation. So we do, if we have to use, we still want to use the same reducer code as far as the combiner is concerned. So what you do is we change our code a little bit, and let's see how we do it. And that's what we'll do in this average example. So for this, we are going to look at posts.xml file. So posts.xml file is a file which is about the posts on Stack Overflow. So there are 2 varieties of posts. One is question, the other is answer. And some of this is reflected in these fields. So post ID type is something which will tell you whether this is a question or an answer. Then there are other fields, user ID, the person who has created the post, creation date, and the body of the post. There are other fields as well. What we are trying to find in this average example is how much an user is contributing to the posts on Stack Overflow. Okay, so in this file we find a number of users who would have posted on multiple occasions. We want to find an average of average length of their posts, and from that judge their contribution to Stack Overflow posts. Okay, so the simple method for this would be again let the mapper give out the key and the value pairs and do everything as far as calculating the average is concerned. Do everything on the reduce without any combiner. Okay, but we want to use a combiner here because combiner can have a lot of benefits here. So to get around this, we have to implement this operation slightly differently, and let's see how we do it. So instead of just outputting the count from the mapper, what the mapper will do is is going to output an average and a count value. Okay, and what we actually do is, as far as the count is concerned, we emit count equal to 1 and average equal to the post length for each input value into the mapper. Okay, just by doing this little bit of a change, and then this is creation of uh, a composite object in slightly different way, in which you have put a count, you have put an average. Just by doing this and manipulating the way you were calculating the averages, we are able to use the same reducer as the combiner. So on this slide, combiner option code associativity is preserved with little modification to the mapper and the reducer code as suggested. So you can use the reducer as combiner with that modification. And I will show you the code for that. So count average tuple is the object which you output as a value, in which we have this count and the average we talked about in the last slide. Look at so here's a key, which is the user ID. Then in this outCount average object, we are setting two values. One is the count, which is always set to 1 when it's output from the mapper here, and then the average we are just setting to the length of the body. Okay, with this modification, let's see on the reducer side now. So it's what it's doing is it's multiplying the count it has got from that value object and multiplying that average. So count and the average is multiplied. With that you get the sum, and then you do a running count of all the values that the reducer has got for this group key, and then you set this in the result, the count and the average, which is output of the key. And then we can use the same reducer code as the combiner. Yeah. Now we can use that. Associativity is preserved now. Let's run this part of the code. Give me a second. I'm just trying to do some setup here. We're running this program on this data set here. Yeah, so here's the output. So these were the user IDs, and this is the average length of the posts from these users and how many posts they have done. So again, this is, as I said, another summarization pattern. You quickly have an idea as to which users are contributing more to the posts. Let's see if you have some questions on that. Okay, so we have this question again. What's the associative role here? So as I said, right, so average operation in itself was not associative. Okay, so if you had moved all your data from the mapper side and the averaging was done inside the reducer, you would not have been able to use the same combiner as the reducer. Okay, because the average operation is not associative. So my explanation to that was, if you have 5 numbers, 1, 2, 3, 4, and 5. All right, so calculating the average of these 5 numbers, you would sum these numbers and divide by 5, right? Now, look at the other side. If you, for example, if you combine 1 and 2, and then you combine 3, 4, and 5, get the averages separately, and then when you have these separate averages, 2 separate averages, and you take an average of these 2 things, in the end, these 2 averages, the average you will get ultimately, it's not going to be the same which you calculated on this whole data. Okay. Which means that 1 plus 2 plus 3 plus 4 plus 5 divided by 5 is not equivalent to 1 plus 2 divided by 2 plus 3 plus 4 plus 5 divided by 3, and this whole thing divided by 2. Okay, that's where the associativity actually breaks down if you are doing average. So average operation was not associative, and we could not have used that as the combiner. So what we did is we went ahead and made modifications to the code. Okay, so what we did is we, instead of sending out just the average, we started sending out the count as well with that. Now if you have the count and the average value, you can definitely multiply these two and you get the sum. Okay, so once you have the sum with you and you have the count, running count with you, you can do those calculations, right? Either in the reducer or in the combiner. Now with this change, I can go ahead and use my same code which is there in the reducer as a combiner. Does that help? Okay, so let's take that stuff offline. Probably on the forum we can discuss that and move ahead. If there are questions from others here. Yeah, please go ahead. Yes, what's the question? Yes, so the leftover, let me paraphrase that. What we're asking is you have two different types of group keys, and the combiner does not execute a couple of rows, and then what will be the input to the reducer? Of course, reducer is not run on any of those key value pairs, then those things will go as it is towards the reducer side. Okay. Okay, thanks. Okay, now moving on to the next one, that's counting of the counters. Uh, uh, okay, here we use, so I guess folks who are already involved with Hadoop definitely know about the counters. So this is another kind of design pattern where we use just the counters to accomplish things which otherwise you would have reducers and transferred a lot of data across the network to get accomplished. So the benefit of using these counters is that everything happens entirely on the map side. No reducers or explicit code for summing is required. You don't have to do any summing yourself. The framework takes care of that. You will define your own custom counters for these to work. And it's the Hadoop framework itself keeps track of those counters. There's a caveat to using these counters. That is, you cannot be using too many counters in your program, because it's being masked. For example, if you are talking about MapReduce version 1, so in those cases the job tracker is responsible for keeping track of those counters, and it has got other jobs to perform. So if you increase the number of counters to a lot, then the performance of your whole system starts to get affected. So you have to make sure that if you're using this pattern, limit your counters to tens, maybe 20, maybe 25, not more than that. Maximum 100. Actually, you should not be reaching those limits, but generally it should be somewhere around 20s or 30s, not more than that. One of the users could be how many times top 20 users posted to a Stack Overflow last month. So you could use it for this purpose. So you know there are 20 different users, so 20 different users for whom you actually want to figure out how many posts were there. So you will end up creating 20 different counters, and in your program, on the mapper side, whenever you find that user, you increment that counter, and rest of the things will actually be taken care of by the framework. This is the structure for counting with the counters. So you start with the mapper here. All the tasks, whichever is to be performed, happens in the mapper only. There's no reducer here. So incrementing counters A, D, and B over here, A and C over here, counter D and B over here. And then these actually are tracked by the task tracker, and ultimately these things go to job tracker. And that's where you will see your output coming from, back to the client from the job tracker. This is the mapper which I just explained to you. And the benefit is there's no combiner, no partitioner, no reducer. So you're saving a lot of effort on that side. And the thing to keep in mind is there's no output file as such written, but you need to have an output. So in terms of performance, because most of the task is being taken care of by the framework, so the counters are generally very fast. Because you're not doing any network traffic here by transferring data to the reducer side. So from that perspective also, this pattern is very fast. So it's mostly on the number of map tasks being executed and the complexity of the mapper code. The use cases are quite self-explanatory. Count the number of records for over a given time period. So, for example, in 24 hours, you want to count the hits to your website, for example. Then you could use, because here you will require 24 counters for doing that. Okay, and then the size is not increasing too much. But if you remember the word counting problem, right? There you could not have used the counters simply because the number of terms which you're dealing with over there is much more larger. Let's look at one of the examples for counting the counters problem. And the data which we'll use for this is votes.xml, again part of the Stack Overflow data. So some of the fields in this is post ID, vote type ID, creation date, and user ID. And we are going to create counters, 3 different varieties of vote ID type. So we will create counters in favorite, offensive, and spam. Okay, so the program in the mapper is very simple. What you do is you read your records, and if you see that you have one of these values in the vote ID type, then you increment the corresponding counter. Framework will do rest of the things for you. Let's see the code for this. So here it is. I have this counter. One second. Okay, so here is where you actually define your custom counter, which is called the votes counter, and it's got 3 different values: favorite, offensive, and spam. And depending on your record in the code over here, you increment these counters by 1. Okay, when your program finishes over here, so you have a code which is 0 successful completion, then you visit each of these counters and print their values. That's what it is. Let me run this example. Give me a second. Okay, so I'm running that code now for you. Yeah, so here are the values. So there were 391 favorites, 1 offensive, and spam was 0 in this small data set, because I have a very small subset of the bigger votes.xml, which is much larger in size. Okay, so yeah, so there's this question on, does mean and standard deviation problem fit into numerical summarization patterns? Yes, it does. And I have not covered that because of the paucity of time, because I have to cover other things as well in this class. But there is a reading which you can do after the class and understand the median and the standard deviation based on that. So I'll leave that as a further study for you, and I will give the reference of the book. Any more questions so far? Okay, I need to understand how pattern is going to resolve memory issue. Yes, we have something which we'll discuss. Actually, that's part of your project. So after this, I'm going to be discussing the inverted index. And so one version of the inverted index we're going to discuss in this class. And then as part of it, you will do some scalability hacks to that to make sure that the memory issue doesn't arise. Okay, a lot of other folks have gone quiet. Okay, so it's in terms of the understanding, am I clear enough so that you're able to understand this? Okay, I need a few more answers. Okay, okay, fine. So what I would also encourage is on the forum, be active on that, and we can have a lot of discussions on those forums as well. If you haven't picked up something in the class, and if the questions haven't come through in this class itself, we can definitely do it over there. Okay, okay. Yeah, it takes a bit of an understanding. So somebody has, the concept is clear, but need to analyze code, as I'm new to Java, which is fine. Of course, any new thing will take some time to observe. Yes. So as I said, I will come to the project slide sometime later in this lecture, and there, what you will do as part of the project is mostly a real world. Actually, you will end up developing a search engine, rudimentary search engine, where you will use a scalable inverted index, and you apply the page rank algorithm or the graph algorithms on MapReduce, and you will use that along with some of the filtering patterns, join patterns, and the sorting patterns. So that probably would be a real world scenario. I want to keep the class itself, the examples that I give in the class, still, I mean, these are not toy examples because the data which I'm using is still from Stack Overflow, and some of these analytics, and today we are just talking about the summarization part, right? So these things are going to be useful for folks who deal with such data. Okay, so let's move ahead. How are you keeping your time? We have, I guess, another 1 hour to go. Okay, that brings us to the last design pattern that we're talking as far as the summarization patterns are concerned. And I would like you to think about these. These are complex problems, right? As I said earlier, inverted index is a complex problem, but we can solve this very simply using the MapReduce design pattern. So in general, what inverted indexes actually do is it's a data structure, okay, and it's sort of a map from terms to a list of identifiers. So for example, the Google search engine. So if it has looked at millions of documents, by reading all those millions of documents, it has created a map from those terms to the doc identifiers where those terms actually happen to be. So that's where the inverted index pattern comes into picture, and the purpose of doing that is to make the retrieval efficient. Okay, so when you do your search queries, they actually go into the inverted index, and that's where the search is made, and then the right documents are returned to you. Of course, before that, there is a page ranking, and that's something you will implement as part of the project. So that's also something which is done. Not as part of your query, but it's done in the background already, so that information is stored statically. So as far as example for inverted index is concerned, we just saw, right? So search engine was one. The other is in text analytics. So you could also create, so in text analytics, we do a lot of annotation on the text. So for example, we try to figure out which of the entities which is mentioned in this document is actually a person, which is a place, what is an organization. And then we can do multiple, for example, which of these is actually historical information. And then such information in the text is tagged. Okay, so if you're looking sentence-wise in a document, a sentence can end up having multiple annotations on top of it. So we could use inverted index pattern over here, where the pattern would be from the sentence to the list of annotations which happen to be on that sentence, which will make the retrieval easier. Here is the structure for inverted index, a very simple structure again. So you have the mapper, which is taking the input split and which is being read by the record reader, and it's outputting the keyword, each of the words in the document, and along with that it's outputting the document ID. From there it moves to the partitioner, and then reducer gets all this stuff, and the job of the reducer is again very simple. It gets a group of keys, and for each of those groups it combines the list of IDs together, and then things are output. So in terms of the structure, as you see, a very complex problem on this framework. Solving this is pretty simple. Of course, if the simple initial simple solution that will have scalability concerns, but that's what you slowly improve on algorithm is concerned. But the basic algorithm for doing an inverted index structure is what you're seeing just right in front of you. Okay, so when we are talking about the numerical patterns, there the combiner was very useful. Why was it useful? It was useful because we are calculating a statistic, a summary of the data, right? That was the purpose of those summarization patterns. Here, combiners are not going to be very useful for the simple reason that you have to ultimately you have to send all the data that you have out of the mappers to the reducer side. Okay, so for example, if mapper 1 is outputting a term like structure, for example, look, structure happens in document 5 and the structure happens to be in document 7. Even if you use a combiner and combine these two together, still you will have to send that data across to the other side to the reducer. So as far as network traffic itself is concerned, it does not make too much of sense to use combiners in inverted index. And especially when you're using identity reducers, right? In identity reducers, you just output whatever value you have for a key. You just output those values out. There's no computation and written code which is there by you. Okay, but there are some cases where you want to do some kind of a concatenation of the data before you push out. And actually in the code which I'll show you, there we do a little bit of a concatenation, and for that purpose we can use combiner. Although in terms of the effect as far as the network traffic is concerned, there's not going to be much of a use, much of a difference, I would say. Using a partitioner, of course, is useful, and I guess if you are writing an inverted index on really huge data, then custom partitioner should along with that, you should also use a stopped word list. That is the things which need to be removed from your terms list before you output these data into the inverted index. Because, for example, these kind of terms would happen a lot in the document, and if you do not remove these stop words before creating an inverted index, you will end up having a lot of junk data in your inverted index on the other side. So some of these things should be removed up front. Okay, so what is the performance of inverted index? Okay, so again, the cost as far as grouping by keys and all those things is concerned is still the same. Most of the cost here is the parsing inside the mapper, and this becomes because when you're talking about big data, for example, a Google search engine, there a lot of parsing has to be done in the mapper side. Because text analytics has to happen on the mapper side, from where you get the right kind of contents, and then based on that you push things into the inverted index. So the cost is going to be dependent on the kind of parsing you are going to do in the mapper. Actually, if you are just doing a word counting, then probably the cost is not too high. But if you're doing a lot of text analytics, for example, one of the annotation examples which I gave to you, they can be pretty costly. Hotspots in the index keys, they are not uniformly distributed. So yeah, this is something which I just talked about related to partitioners. So you should find out the hotspot in the index keys and make sure that you write a custom partitioner so that the keys are uniformly distributed to reducers. Inverted index use cases, Google search engine, that we already know about. Wikipedia reference inverted index. This is actually coming from the Stack Overflow data itself. So what happens in the Stack Overflow data is a lot of places people have these links to Wikipedia. You could go ahead and create an inverted index of the Wikipedia links, which is the key, and all the places in the posts on the Stack Overflow where such Wikipedia links are mentioned. Okay, we can create an inverted index like that, and such things can actually be added at the end of the Wikipedia page. Okay, so you have additional information on the Wikipedia page as to which pages on the Stack Overflow talk about are also discussing this particular link on Wikipedia. Maintaining additional annotated information on terms. So, and this I had explained in previous slides. Creating index and a Stack Overflow data. This is one component of the project work. Yes. So I will in this class I will show you an example of an inverted index, but that version is not very scalable. As part of the project, you will modify this and write a scalable inverted index, and I'll show you pseudo code of that so that you can get started with having a look at it. Okay, so our data set here is the posts and the comments files, and the idea is to create an inverted index from terms found in posts and comments to the documents in which they refer. They are present. So a term, and then the value for that will be a post ID or a comment ID. Okay, so let me show you the code for this. Okay, so let's look at the mapper here. I have got a setup method over here in which I'm distributing the stop words file. I've got a stop words file, and those stop words I want to remove from the data on which I'm going to do the processing. So, and that stop words I distribute in the distributed cache. So over here, in the made class, I add the cache file, stop words cache file, and then read this in the setup method for the mapper. Okay, and then I create a map of, so this is actually an array list of stop words, which we'll use in the mapper to ignore such words. Okay, this is, so some of the code here is, the post, as I told you earlier, contains both the questions and answers. Some of these will be about questions, some of those will be about answers. I'm trying to distinguish these two types along with the IDs for those posts. So I say post ID along with the question, along with this tag question, and post ID along with this tag answer, or along with comments. Okay, so that's the code that you see over here. And then I get all the words in the string, array of strings, by splitting that whole text document. And then the code here is very simple. We are actually not doing much. For each word, I'm just setting the value which is the row ID for that document. And that's being written using the context object. In the reducer code, you take the ID, which is the term, and then we add the values. Okay. One thing which is missing here is generally when you are creating an inverted index from a term to the set of values, you will want these values to be sorted because that will aid in a retrieval process. The problem which happens is to sort now this whole MapReduce framework sorts only on the keys, not on the values. So the sorting will ultimately have to happen in this reducer, and for that purpose the reducer will end up using some kind of a list, some kind of a structure, and if there are terms which tend to have a lot of documents in which they appear, then this becomes a scalability concern, and that's what is a problem in this code. We are not doing any sorting here, but still there is a problem here. For example, doing the string builder also, you could, I mean if the size of the values that just deal with is just too many, you can end up having out of memory errors here. So this is what you will modify to make it more scalable. Okay, so that was the code. Let me show you the demo for this. Give me 5 seconds. So we run this. Okay, so the output. Okay, so we have not cleaned up the data. So the inverted index has been made. So for example, this was taken as term. Our data was not very clean. We didn't spend time on cleaning the data. So this was taken as a term, and this happens to be in this document ID, and this was an answer. Okay, it's been being printed 4 times because we did not take care of that in our algorithm. So wherever this term has happened to be present, this actually happened 4 times in the event, so it's printing it 4 times. Okay, but this is, it's not very legible to look at, but this is your inverted index which has been output. And this is right. I mean, in terms of the output and correctness, this is fine. We need to do further things as far as cleaning the data itself is concerned on our side to make sure that the gibberish doesn't appear. Okay, let's see questions. Any questions on that? I see silence. Is it understood completely? Okay, let's move ahead. Okay, so now we come to a description of the project work. You will design and implement a rudimentary search engine on Stack Overflow data, which will involve writing code for a scalable inverted index. And I'll show you a pseudocode for the first one. Then we'll write a PageRank algorithm, and this is the graph. You'll use some parts of the graph design pattern here. And this will be done in 3 different parts, which I will explain to you tomorrow. The first part, which we'll start doing tomorrow, will be around creating a data structure, a graph data structure for your stack data on which you will operate. Then you will also write a Bloom filter. This will be discussed tomorrow. And partitioning and sorting and joining, all these things will be used as part of your project. What I will do is in each of these lectures, I will explain to you one component of the project which you should start implementing. Probably by tomorrow you will have an idea about 2 different modules. So scalable inverted, and as far as PageRank algorithm is concerned, you will have an idea as to the data structure that you have, in the graph data structure that you have to implement, on which you will implement the PageRank algorithm. So those things, 2 things would be clear by that time. And of course the Bloom filter will also be discussed tomorrow. Then in later classes next week, we'll talk about the partitioning and the sorting and joining. Actually, if you look at the course schedule, the graph design patterns were scheduled for session 5. But because we need to start implementing that early, I will have to start explaining to you a little bit about those modules in each of the classes. So tomorrow I'll explain a little bit about the first part that you have to implement in that, and in subsequent sessions I will explain further things. So as you can see, you will end up using quite a few things which you discuss in this class, and ultimately we'll do a search engine. Of course, not at the same scale, but something which will let you understand what goes into making such complex products, and some of the most complex algorithms which are used on those can be implemented quite easily on this pattern. Although if you look at PageRank algorithm, that's a graph algorithm, and again, all these require iteration. And as I said earlier, framework is not actually well suited for iterative framework, but we can work around those problems and do a pretty efficient implementation on MapReduce as well. Okay, so the data set that you use for the projects, these are the files. You have posts.xml, comments, badges, post links. Post links is the one which you'll use for page rank. These are the links that are present in the posts, pointing to other posts. And we'll use that structure to create the graph. Users, these are self-explanatory, votes, tags, and readme is a file which actually explains all these files in detail. I have not put these data so far into the place where you need to look for, but I will truncate some of that stuff and there soon, maybe tomorrow or day after. Okay, so now we come to the first module for the project, that scalable inverted index, and let's see how you can make your code scalable. So the basic inverted index that we saw has some scalability issues, and that was regarding doing sorting inside the reducers. How do we avoid that? And that's what we'll do here. So reducer emits key equal to term and value equal to the list of document IDs. These document IDs, as I told you earlier, should be emitted in a sorted order for efficient retrieval. The MapReduce framework itself does not do a sort by value. So reducer was doing that in-memory sorting, although in our code we didn't do that sorting, but generally it should be done, more efficient retrieval. Now if you start doing that sorting algorithm tends to use large lists. And for large data sets on a term, this can lead easily, very quickly lead to out-of-memory issues. So we look at the variant of this basic inverted index. Okay. And let's see how we'll solve that. What's the requirement for a scalable inverted index? So avoid running sorting inside the code. We'll avoid that. Instead, we'll use another design pattern, which is value to key conversion design pattern. So at the start I had told you in the mappers, the key and the value which is output, there is some significance to that depending on the kind of problem you're trying to solve. And the value to key conversion here actually uses that concept. Okay, and we'll see what value to key conversion design pattern is. And when we use value to key conversion design pattern, we'll also have to use a custom partitioner. Okay, so this is one part which we'll do to make our inverted index scalable. Then in the retrieval doc length is used to inquiry document score. Okay, fine. So when you're trying to retrieve documents, one of the parameters to choose which document to return to you is also the length of the document. Okay, now that length of the document needs to be calculated. You could easily do it as a separate job, MapReduce job, but we'll use another pattern which is called the in-memory combiner pattern, so that you can do this length calculation as part of the inverted index pattern itself. Okay, so let's now I will be showing you pseudocode for these in-memory patterns and the value to key conversion patterns as they are used inside the scalable index pattern. Okay, I'll just show you pseudocode for that, and you have to do the actual implementation for this, but I'll explain in a couple of slides what these patterns are, and these are very simple. So in-memory combining is about incorporating combiner functionality directly within the mapper. So we are not using any here. Okay, so some of the combining which could have been done by the combiner, we shift that functionality back into the mapper. So what are the advantages of this? So on a combiner itself, you don't have any control, right? So it's a framework. It depends on the framework. If the framework wants to run it, it will run. Otherwise, it doesn't. So you don't have any control over when the combiner runs, whether it runs or not. But if you do a local aggregation within the map, you have that control. You have that control, right? So you're able to have some control over this. So you do your aggregation in the mappers, and mappers generate only the key value pairs that will ultimately go to the reducers. Okay. There are certain disadvantages to doing this, and that's the first thing is MapReduce is about programming. It follows a function programming model, and you're breaking this because what's happening here is you are sharing the state across two different input key value pairs when you are shifting the stuff into the mapper. This can lead to ordering dependent bugs as behavior depends on the order of input key value. A scalability bottleneck due to storing of results till all the key value pairs in this input split is done. Yeah, so here's the problem. So we were trying to incorporate some of we're trying to solve some of the scalability problems, and along with that we said that we'll calculate something else, and that's the length of these documents, so that should help us rank these documents easily. And then we start hitting a scalability bottleneck right on the mapper side. These are some of the disadvantages also of using combiner, but not to the same extent as a sorting on a term with a lot of document IDs would incur inside a reducer. Okay, so just hold on to this demo stuff because I will explain the value to key conversion, and then in the same page I'll show you both these patterns being used inside inverted index. So value to key conversion is about moving part of the value into the intermediate key to form a composite key. So what you do is because the framework does not do any sorting based on the value, what you do is you shift the value part on which you need the sorting to be done and make a composite key along with the key itself. So after doing this, the framework will take care of sorting your data rather than you doing it inside the reducer. But one thing you have to keep in mind is that you have to go ahead and implement a custom partitioner now because you want to make sure that for each of the keys, for each of these terms, you are aggregating everything related to this term on the same reducer. It's important to understand this because you could end up, what could end up happening is you have combined the value with your term, and then if you don't have a custom partitioner, if you use the default partitioner, that can end up sending your terms with the same value, same terms, say as the group key, to different reducers. So, it's not only the key that you have, you have also combined the value along with it. So you need a custom partitioner over there. Yeah, but one of the downsides is now you have many number of intermediate keys for the framework to sort. See, if you had, for example, if you had 5 terms that you're dealing with earlier, and there were five values, maybe 10 values. Okay. Now, so the framework had to deal with 5 different keys. Now, because you have combined these together, now you have to deal with m cross n. That's 50 keys has to be dealt by the framework. Okay. So let me show you the pseudocode for the skip. Okay. So here is the code. So the mapper gets the document ID and the document. In each, so this is the in-memory combiner which we are doing. What we're doing is, instead of emitting out for each term and for a term and the document ID, is we do that combining inside the mapper itself. Okay, so if this term is found n number of times in this document, that thing is going to be output. Okay, and we also implementing the value to key conversion here, because if you see, now we have a composite key which is the term plus the document ID. We're trying to sort in the reducer on the document ID, and that's the thing which you have created keys on here. And then we have the value side. So on the value side, we have 2 things. It's the count of that term in this document, okay, along with document length. So value is also composite. Okay, so this is something that's just a payload. I mean, it depends on you what you actually want to take forward as far as creating an inverted index is concerned. But I prefer this because let's keep it this way at the moment because we might use the document length as well as one of the parameters to come up with a ranking as far as the page rank algorithm is concerned. So let's keep it there at the moment. Then on the reducer side, here is a code. So there is a setup here and a close method. So what we are doing here is we are, okay, so these are the keys and the values. So what we might have is we have one group key, one term. Along with that, we have different document IDs for that term. Okay, and then after that, another sequence start, which is with 2 with the corresponding document IDs. So this is a code which is trying to separate those out and create a list of that. So the important point to consider is the sorting is gone from here. Okay, the sorting is gone from here, and we are just trying to write out values separately for each of these terms. And if you closely look at this code, you will understand because we are basically comparing whichever value comes in, we compare with the previous term. If they are same, then we keep on appending to the same list. And then when we see a new term coming in, which happens here, we immediately write that out to the context. Okay. So that's a pseudocode, and this is what you should use as a framework for implementing your scalable inverted index.